After the torque converter, the next most important component in an automatic transmission system is the valve body. This isn't actually a single component, but an assembly of fluid passages, solenoids, valves, accumulators, wiring, and electronics that executes the control strategy we program into the transmission control module. There's a very broad range of complexity in components used in various valve bodies, and some have components I've not mentioned. But the truth is that we don't need to know every little part inside every transmission in order to gain serious improvements through calibration and upgrades. The valve body delivers hydraulic fluid at different pressures to different components at different times as conditions demand. When we talk about pressure in the transmission, the first item we often reference is line pressure, which is the high pressure feed from any other systems that follow in the fluid flow path starting at the transmission pump. Because line pressure feeds other hydraulic circuits, such as clutch actuation circuits, we should avoid requesting pressures at downstream items like clutches which aren't feasible. For example, if we have 250 psi of line pressure and we request 150 psi at a clutch, there's ample supply of fluid and pressure to achieve that goal. On the other hand, if you request 350 psi at the clutch, still have 250 psi of line pressure feeding that clutch circuit, you'll likely only end up with 250 psi or perhaps a bit less. This comes back to the general rule that fluids naturally move from high pressure to low pressure. At best, we'll equalize pressure between the line pressure circuit and the area we're delivering fluid to. If that's not immediately making sense, hopefully this comparison will help. Let's say a vehicle has low tire pressure of 25 psi, and we need to fill the tires with air until there's 35 psi for safety. If we try to fill that tire with an air tank that has 30 psi in it, we're never going to get more than 30 psi in that tire, right? Now if we try to fill that tire from a hose attached to an air compressor, and the air compressor is running, but currently there's only 20 psi in the tank because it hasn't charged up yet, we'll actually lose tire pressure because air will flow out of the tire into the air line until compressor tank pressure and tire pressure equalize. Eventually, as the compressor continues running, it'll build enough pressure that will get our tire up to 35 psi we wanted. But whatever pressure the compressor plateaus at is the highest pressure you can transfer from that tank into another system. And we can think of line pressure that same way. Back to automatic transmissions. If line pressure is 250 psi and the peak clutch target pressure is 200 psi, we can increase the target clutch pressure up as high as 250 psi. If you give the clutch all the pressure the system can provide and the clutch is still slipping, the next step would be requesting more line pressure in addition to more clutch pressure. In this case, perhaps 300 psi. Hopefully, the pumping components can deliver that, and valves won't bleed the extra pressure back down to the stock 250 psi level. If physical components are preventing line pressure increase, or the clutch still slips even at say 300 psi, we'll talk about upgrades in the next section. As I touched on earlier, some portions of the transmission require different amounts of pressure. Some also need to have that pressure increased or decreased at a specific rate to get the desired effect. There are pressure sensors present in each key circuit of the valve body to allow for pressure control to a given target, data logging, fault finding, and more. Some areas of the transmission require pressures regulated to less than line pressure, but don't have a need to ramp that pressure up and down. Those components can be managed with a simple device like a mechanical pressure regulator with a valve and spring. When pressure into the circuit exceeds the pressure of the spring in the regulator, it bypasses fluid to maintain the desired feed pressure. On the upside, it's cheap, simple, and reliable. The downside is if we want to change the pressure it regulates to, we'll need to get inside the valve body and change the physical parts. The clutches, on the other hand, require pressure ramping up and down to engage and disengage them in a controlled fashion. If we actuated a transmission clutch with a high-flow on-off solenoid and there was no other mechanism to control the rate of fluid pressure increase, we could ramp clutch pressure from 0 to line pressure so quickly that the gear would be engaged in an extremely rapid and violent manner, which would be totally unacceptable in terms of driver experience or component reliability. In order to make transitions more controlled and palatable, various systems are employed. In older or less advanced automatic transmissions, clutches were often acted on by pistons fed fluid by simple on-off solenoids, but a secondary device called an oil accumulator provides a combination of mechanical and pneumatic damping to increase the pressure provided to the clutch piston. The accumulator has a valve and spring, so as pressure increases, the fluid acting on the valve compresses the spring, which as it travels, exposes an orifice that lets fluid bound for the clutch piston bypass it and drain back to the pan. This bypass increases as pressure increases, slowing the rise of pressure at the clutch piston and making its actuation less like an on-off switch. In addition to the level of mechanical control the accumulator provides, some transmissions have additional solenoids that can deliver fluid into the chamber on the backside of the accumulator valve, causing additional resistance to accumulator motion. The more fluid on the backside of the accumulator, the more pressure bound for the clutch piston is needed before the accumulator will move and bleed clutch pressure off. In this way, we can hold the accumulator in place, causing a more rapid rise in clutch pressure up to a certain point, then bleed pressure off behind the accumulator, allowing it to move. This causes clutch pressure increase to slow as it approaches the pressure target. Depending on the specific transmission and control system, this can be coarse and clunky, or it can be relatively good. But modern transmissions have taken fluid pressure control a step further by using pulse width modulated or PWM solenoids, which can precisely control fluid to achieve optimized pressure curves for varying conditions. Knowledge of the intricacies of the valves and solenoids beyond this point is not required to tune a transmission, but I hope that quick rundown gave you a better idea of what's going on inside and why you may find you have more precise control of shift feel with some applications compared to others. Before we move on to the rest of the system, let's quickly recap what we've learned in this module. The valve body is a critical assembly in automatic transmissions, consisting of fluid passages, solenoids, valves, accumulators, and electronics. Its main job is to deliver fluid at varying pressures to different components. Pressure control and transitions are managed through systems like oil accumulators, which dampen pressure increases, though more modern transmissions utilize pulse width modulated solenoids, which precisely control fluid for optimized pressure curves and can help with fault finding as well as tuning.
That was just one of the many modules taken from our automatic transmission tuning course. The information in this course teaches you the core principles behind automatic and dual clutch transmission operation. You'll learn absolutely everything you need to know about tuning your transmission, potentially taking it from something that feels like an uninspiring wet blanket to something that feels responsive, handles more power, and can be customized to suit your driving style. For more information and to purchase the course, click the link to enroll now.